Hello, good morning. We are Group 2 from Section D, and today we will be discussing about Experiments 1 and 2. Before we jump into the discussion, my name is Ziljan Carlo Arteao, and here are my group mates.
Hi, I'm Jeever.
Hi, I'm Irvin Cruz.
Hi, I'm Daniel Chan.
Hi, this is Iris Claveria.
We are going to discuss Experiment 1, the synchronous motor, lab volt power supply, and metering devices.
Experiment, we have two objectives to reach. And one is to be familiarized with the power supply and metering device of LoveVolt. And the second one is to learn the multiple function of the power supply and the metering device of LoveVolt. So here are the instruments and components to use. We need the power supply, connection leads, metering module. That's it.
We can find the power supply by clicking on Equipment, Electromechanical, then we find the 8821 power supply. As we can see the parts of the power supply. Starting at the top left corner, we see the analog voltmeter. It displays the analog style output voltage that we currently inserted. And the power switch. When we turn on the power switch, the power supply now generates voltage through the whole circuit. And underneath it is the special power switch. The special power switch only works when we insert the special wire. And on the bottom left corner, we see the ground terminal and the reset button. We do not usually use it in these experiments. Then there are the neutral terminals and the voltmeter selector. As we can see at the topmost part, there are the pilot lamps. Once we connected the three lines and turn on the switch, we know that all of it is connected and working when the three lights will light up. Underneath it is the voltage control knob. It has a range of 0 to 100. We can access it by clicking and then inserting what percentage of the voltage we would be using. We can see also the two sets of three-phase AC terminals and two sets of variable DC terminal and the fixed DC terminals. The neutral terminal is used for the fixed DC terminals, so be careful. Here it shows the picture of a data acquisition interface. We can access it by clicking on the equipment, electromechanical, and finding the 9062 data acquisition interface. We can see that there is the voltage, the current, and analog inputs and outputs. The voltage is used to measure the voltage while the current is used to measure the current in amperes. And lastly, the metering interface. We can see it by clicking on Instruments. Instruments is beside Equipments in the toolbar. By clicking on Instruments, we go to Electromechanical and then the metering. Then it displays the metering interface.
This is the LabVault software, and this is what you will see upon clicking the software. You will first need a mobile workstation, and you can find this by clicking Equipment, then Electromechanical, and 8110, which is the mobile workstation. To then add a power supply, go to Equipment, Electromechanical, and choose 8821 power supply. Lastly, to add the data acquisition interface, once again, go to Equipment, then Electromechanical, and 9062 data acquisition interface. Of course, we will need the metering module in order to measure the values generated from the connections you will make. You will have to click Instruments, Electromechanical, and finally, Metering. For the variable voltage control knob that is set to 0%, here are some connections asked. Make sure that you don't forget to have a wire connected to the special power switch in data acquisition because it won't work when you won't connect it. Take note that the variable and fixed terminals should be connected properly and into the power supply. Connections should be in parallel when getting the voltage values.
These are the voltages when the voltage knob is set to 0%. As you can see, V12, V13, and V23 remain at a constant value of 216.5 volts because they are located in the first set of AC terminals and form a line-to-line connection. For the voltage across V1N, V2N, and V3N, the value is at 125 volts. The terminals are observed to be line to neutral, so the constant full voltage must be divided by square root of 3, which results to 125 volts for each terminal. The rest of the voltage across the terminals in the second set of AC terminals are at 0 volts because the variable voltage knob is at 0%, wherein the voltage in the second set can vary depending on where the voltage control is set at. For voltage across DC terminals at V7N and V8N, they have voltages of 0 and 150 volts respectively. The variable voltage knob 0% is also applicable to the DC supply terminal 7N, which resulted 0 volts in V8N is at a constant voltage of 150. It is because of the terminal having a fixed voltage regardless of the voltage control. These are the voltages when the voltage knob is set to 50%. V12, V13, and V23 remain at a constant value of 216.5. Since the variable voltage knob is set to 50%, the value of V45, V46, and V56 is at 50%, which is 108.3. Likewise, the values of V4N, V5N, and V6N are also approximately half of the line to neutral voltage from the fixed voltage terminals V1N, V2N, and V3N. For the DC supply terminal 7N, the variable voltage 50% takes into effect, which makes the value of the voltage 72.5, and V8N is still at a constant voltage, which is 150 volts.
Likewise, for the variable voltage control knob that is set to 50% and 100%, make sure that you adjust the voltage control knob to 50% and 100% respectively to yield accurate results. These are some examples because the process is the same as the one with the 0%, although with different percentages assigned.
In this table, the line-to-line voltages V12, V13, and V23 remain constant at 216.5 volts, and the line-to-neutral voltages V1N, V2N, and V3N also remain constant at 125 volts. Now that the percentage of the voltage control knob is up to 100%, it can be observed that the measured voltages for V45, V46, and V56 has increased and is now equal to the measured voltages for the line-to-line voltages in the fixed AC voltage terminals. Similarly, the measured voltages for V4N, V5N, and V6N are now also equal to the measured voltages for the line to neutral voltages in the fixed AC voltage terminals. V7N has a measured voltage of 145 volts, and V8N is still at a constant 150 volts.
In conclusion, this experiment is familiarized with the usage of power supply, data acquisition, and metering interface with the aid of the LoveVault software. The power supply mainly has the AC and DC supplies. Together with it is the voltage control knob that the user can vary depending on their desired percentage to be applied in the circuit. The bearings of the voltage with respect to the voltage control knob percentage are varied in terminals 4, 5, and 6, while terminals 1 to 3 is at a constant full voltage. The terminals in the equipment used should be properly connected with each other to yield accurate values in metering interface, because this will be done so that no further errors will be entertained while conducting the experiment. Next is in describing the data acquisition interface, we can say that it acts just like a digital or analog ammeter and voltmeter, but an interface in the software. It is simply because in the metering window, the user can see all the voltages and currents they are trying to measure. Moving on, we will now be discussing Experiment 2, the synchronous motor as a prime mover. The objectives of this experiment is to learn how to operate the three-phase synchronous motor and to use the synchronous motor as a prime mover.
So the instruments and components to be used for the experiment 2 will be the power supply, connection leads, metering module, and with an additional synchronous motor generator, prime mover dynamometer, and of course to connect these two, we're gonna use the timing belt. So for the procedure, the front face of this is the front face of the synchronous motor generator. It is located in the equipment tab, then the electromechanical, then choose the 8241 synchronous motor generator. Also, note that there are 3 separate windings connected to terminal 1, 4, 2, 5, and 3, 6. These windings are identical and located in the stator or the stationary part of the motor. The 3 windings carry AC current and will connect to a 3-phase power source. The winding on the rotor or the rotating part of the motor is connected to connection terminal 7 and 8 through a 150 ohm rheostat. So the first step is to connect the fixed AC power supply to the ammeter, then to the generator load. Also, connect the data acquisition interface to the power supply. Connect the fixed voltage power supply to the rheostat load and set the load to 0%. Also, don't forget to turn on the supply and the motor should start running immediately. Note that 3 current meters now has a reading. So to set the minimum resistance for maximum DC excitation to the rotor, so you need to turn the knob for the exciter to the 100%, and the value that should we get is 0.269 amp for the I1, I2, and I3. While for the maximum resistance, for minimum DC excitation to the rotor, you should turn the knob fully counterclockwise, and the value that we should get is are the 0.360 amps for all the current readings. Also, to set the minimum stator current, we got the value of 0.6 amp at a control knob scale position of 68 to 70%. So we can proceed to the lab vault so that we can simulate the experiment.
Now for the next procedure, we are going to use the dynamometer. To locate the dynamometer, we click on Equipment, then Electromechanical, and then find the 8960 prime mover or dynamometer. The dynamometer measures the speed of the motor as we vary the DC excitation. So here, we can see that we need to connect the special wire from the data acquisition interface to the prime mover. We cannot measure anything if there is no connection between the two. Next slide. But first things first, we need to open the front panels from the synchronous motor and the prime mover to connect the timing belt. Because if we do not connect the timing belt, the synchronous motor will just be running and the prime mover will just be in static position. As we can see, for the minimum excitation, we got the value of 1,800 revolutions per minute. And at the maximum excitation, we also got 1,800 revolutions per minute. In letter C, the speed at the minimum stator current, the speed is also 1,800 revolutions per minute. The rotation direction from the experiment is clockwise. And does the speed remain constant? It's a yes. Because it remains constant because the synchronous motor, whatever load it has, will have no bearing on its speed because it is constant and synchronous. As we can see, we use the data acquisition interface to measure the current. And to measure that current, we need to parallel the data acquisition interface to the prime mover. That's why we got the value of 0.235 amperes. The rotation of the synchronous motor and prime mover changed to counterclockwise. It changed to counterclockwise because it reversed in polarity. It reversed in polarity because we interchanged the terminals 1 and 2.
So to prove that all data presented are correct, we can recheck the LoveVault software by doing the experiment proper. So first, we need the power supply. Then the synchronous motor generator and the prime mover dynamometer. Also, the data acquisition interface. From the procedure as discussed, we must connect the power supply, AC power supply, in series with the ammeter, then to the synchronous motor generator. Then the next step is to connect the fixed DC voltage supply to the rheostat of the generator. Keep in mind that this is a DC voltage, so a change in polarity might change it or might have an effect in the data gathered. Also connect data acquisition interface to the power supply. Lastly, connect this in Y. So, as measured earlier, at 0%, we must measure a 0.36 amp. And when we hit the max exciter, we must get a 0.269 and for the second part of the experiment, which includes the prime mover and dynamometer, we should connect this prime mover with the power supply through the data acquisition interface. So after waiting for the synchronous motor to stop, we should lower the front panel and connect the timing belt to the prime mover. Raise the front panel and turn the power supply on again. As you can see, we measure a 1,800 revolution per minute at a maximum exciter current. So, maximum exciter. So even in minimum or fully counterclockwise, we are still measuring 1,800 revolution per minute. Also, at the minimum stator current, which is in 68 to 70%, we are still measuring 1,800 revolution per minute.
In conclusion, dealing with synchronous motor that are connected in three-phase source, here, The synchronous motor connected in three-phase source will send the same magnitude. However, we observe that when it is in three-phase, the angle of each magnitude changes. Next, the measurements that in the three-stator winding current also varies whenever the DC excitation is in minimum or maximum. It is because when the rheostat is in maximum, this just means that the current is low because the DC exciter exhibits the minimum value resistance. On the other hand, when the rheostat is in minimum, this is simply because the DC exciter exhibits maximum value resistance. Next is the prime mover or dynamometer is connected by a belt to the synchronous motor or generation. It is because to measure or determine the speed of the motor together with the changing percentage of the DC excitation. The values gathered for all data considering the maximum, minimum, and even including the stator current is fixed. Lastly, the AC voltage is applied to stator, which produces a rotating magnetic field, and DC voltage rotor is connected to rotor, which produces a constant magnetic field.